Okay, so good afternoon to all, and welcome to lecture number 11. And in today's lecture, we will be studying the problems on translational mechanical system. Yesterday, we talked about this one, translational mechanical system, in which we studied how to obtain the mathematical modeling of three basic elements which are used in mechanical system, like as a damper, or it is also called as a dashpot. Then second one is spring element, and third one is mass, okay, or moment of inertia. So that we have studied how to obtain the individual mathematical model of every component. So you know that, suppose for example, just okay, to revise it, first two slides I'll revise it, and then after that we'll start our today's topic. So this is basically a damper or dashpot, which I have told you yesterday, just like as a shock absorber or brake kind of system and so on. So there is a basically piston here, and then so when you apply a force on this one, so definitely this is constant, so definitely this portion will move to this side, or if it is force is in this direction, then this will get displacement in this direction and so on. Now here, one end of this dashboard, say there are two ends. One is this one left hand, and another one is right side end. Now, if left side end is at a reference or it is fixed, and then if you are applying a force on this one, so only right side end will get displacement. And then if that displacement is x, then this force and displacement relation will be equal to F is equal to C into x dot, where C is the coefficient of this dashpot, or this one damper and so on. So this x dot is nothing but the derivative of displacement, and derivative of displacement is nothing but the velocity. Means here force is directly proportional. In case of dashpot or damper, force is directly proportional to the velocity. So that we have studied yesterday. Now, if the both ends are at open side, like means there is no fixed end, like x2 is not fixed, okay, this end is not fixed, or this end is not fixed, and then if you are applying a force on that one, then the relation between the displacement and force is given by this displacement minus this displacement. So F is equal to C into x1 dot minus x2 dot. So this is the derivative at, or velocity at x1 minus velocity at x2. So it is directly proportional to the difference of velocity basically. And the proportionality constant is C. C is nothing but the coefficient of that dashpot and so on, right? Now, when two dashpots are connected in parallel, yesterday we have studied that when two this one springs are connected in parallel, then overall this one equivalent coefficient of spring odds k1 plus k2, and if they are connected in series, then equivalent to odds k1 k2 divided by k1 plus k2. It was just like as a when resistance are connected in series, okay, you know that total resistance will be equal to R1 plus R2, and when resistances two resistances are connected in parallel, then it will be R1 R2 divided by R1 plus R2. So it is exactly opposite relation in case of dashpot as well as this one spring element, if you compare that one with resistance and so on. So here, if they are connected in parallel, then there will be addition. But in case of resistance, when they are connected in series, then there will be addition. So this was, if it would have been resistance, then this we would have got as a R1 plus R2. But here, this one dashpots are connected in parallel. So equivalent coefficient of dashpot or damper will be equal to C1 plus C2. Similarly, if two dashpots are connected in series, then this will be equivalent coefficient of dashpot will be equal to C equivalent equal to C1 C2 divided by C1 plus C2. So that you have to remember and so on, right? Then already we have studied yesterday about this one individual spring element, and then dashpot element as well as mass element. Now here we are considering the example, first example as one is there is a reference element, and then spring is connected. One end of the spring is connected to the reference point, and another end of spring is connected to the mass element, right? So this one Now, if you push this mass, definitely there will be opposite force offered by this one spring element, and then this force of mass and this force of spring will be same. So what is the force on the mass? That is equal to m into x to x double dash. That is nothing but the acceleration. And what is the force due to spring? So that is equal to minus k into x. Okay, because this is in opposite direction, that's why minus k into x. Now if you take this side, so it will be equal to 0. So if you add the force of spring element and mass element, it will be 0, right? So this is just simple example I have given you here of spring and mass system. So this is spring, and then another end of spring is connected to the mass. So definitely the spring force and mass force must be same and opposite in direction. If you are okay, so mass element is, if you are pushing in this direction, definitely spring will give opposite force like in this direction. So that's why this minus sign is there. And if you are pulling, then definitely again spring will also give opposite direction force. So this is the mathematical model of this simple system. Now consider this equation or this example, okay, which is also very simple. Now see that what is there. See, this is nothing but the reference. Okay, so this is nothing but the reference. Now see that here one end of spring is connected to the reference point, another end of spring is connected to the mass. So this is mass element having coefficient equal to m. This is the spring element having coefficient equal to k, and then displacement is in this direction, x direction. Now here you have applied the force. Now when you are applying the external force, so definitely there will be opposite force offered by this mass element, as well as there will be opposite force offered by the spring element, right? So see that if you draw the free body diagram, force free body diagram, then see that on this mass, this force is in from left to right. F force is from left to right as it is. And when you apply this force, this one left to right force, if you are applying, then definitely there will be opposite force offered by this spring element. So this Fk is nothing but the opposite force offered by the spring element. Similarly, this mass will also resist to this force F, and this mass force is given by Fm, which is in opposite direction. Now see that this F force is from left to right, and the opposite force offered by spring element and mass element is from right to left, right? So this F must be equal to, means total incoming force must be equal to total outgoing force, right? Or this F must be equal to the summation of Fk and Fm. So where Fk and Fm are the force applied by the spring. So Fk is the force applied by the spring, and Fm is the inertial force of this mass element. Okay. Now see that. So this is the free body diagram we can draw for understanding purpose. Now we can, after that, we can write the equation, force equilibrium equation. So see that this F is basically from left to right. Fk is the force offered by spring element, which is in opposite direction to the F. Fm is the force, reactive force offered by this mass element, which is also opposite in direction of F. Now this F force must be equal to this Fk plus Fm, because these two forces Fm and Fk are in same direction, so they will get added. And this F is in opposite direction, so this total applied force must be equal to total opposing force. So F is equal to Fk plus Fm. Now we know the equation of this Fk, and also we know the equation of Fm. So how do you find the this one Fk, this one force? So definitely if x is the displacement here, then you know that force offered by this spring element is directly proportional to the displacement. So we can write that as a k into x. So see that this Fk is written here, okay? So which is directly proportional to the displacement. Similarly, the force offered by this mass element, which is Fm, which is written here, which is directly proportional to the acceleration. So acceleration is nothing but the double derivative of x. So I have here written as x double dot. So this force F is equal to m into x double dot, which is nothing but the acceleration. M is nothing but the coefficient of this mass element, plus this Fk is nothing but which is equal to k into x. So where k is the coefficient, spring coefficient, and x is nothing but the displacement. All right. Now, if you take the Laplace transform of this one by assuming zero initial condition, so what is the Laplace transform of this f of, see, this is all those things are in terms of time t. So f of t will be written as a f of s. Now this m is constant, so which is written as this one m, but this one x double derivative is there. So you know that the derivative in a case of Laplace transform is replaced with s square term. So s square is because of this double derivative, and then x of s will be as it is. So this is the Laplace transform of this term, right? This is the Laplace transform of this term, and k is constant, so k I have written here. What is the Laplace transform of x of t? So that is equal to x of s. So this is the overall equation of this one mathematical model of this system, which is given here, like simple spring element which is connected to the mass element, and then to this mass element a force is applied. So what will be the mathematical model of overall system? So that we have derived. So for that, what we have done, first we have drawn the free body diagram. So when you are applying the force on this one, so there will be opposite force offered by this spring element. Also there will be reactive force offered by this mass element. So this spring element is from right to left. Also this mass element force is from right to left. And then after that we have written the equation for force, equilibrium equation, which is equal to F. This right to left force must be equal to left to right force must be equal to right to left force. So right to left force there are two forces, Fk and Fm, so which will get added because they are in same direction, and F is from left to right. So this F is equal to Fk plus Fm, and we know how to find out the individual Fk. Yesterday we have studied that one. Fk is equal to k into x, and we also know how to find out the individual force of mass element, which is nothing but m into x double dot. Right now, after that, what we have done, we have taken just a Laplace transform of this equation. So all those terms are in time domain. So if you take the Laplace transform, this f will be replaced as f of s. Then m is constant, so it will be replaced as m only. Then x double dot is nothing but d2 x of 2 by dt square. So you know that d by dt square is a double derivative. So in case, Laplace transform double derivative will be s square. So this s square term will be there, and then x of t will be nothing but x of s. Then this k is constant, then Laplace transform x of t will be equal to x of s. So this will be the mathematical equation of it. Now so this is mathematical equation of it. Now you know that what is basically input. What is input here? Input is force. What is the output? The output is displacement. Now if somebody asks you that you find out the transfer function of this system, so what is transfer function? Transfer function is nothing but it is the ratio of Laplace transform of output variable to the Laplace transform of input variable. Now which is output variable? Output is displacement. So x of s is the output variable. What is input here? Input is force, so f of s. So what you have to find here? X of s by f of s. Now you know the equation which you have derived here. F of s is equal to m into s square x of s plus k into x of s. So you can take the x of s common here, and then x of s by f of s is nothing but the transfer function of that system. So transfer function of that system, x of s by f of s will be equal to 1 by ms square plus k. I hope that you have understood how this this one transfer function of that given system is obtained. Now see that now suppose for example how many roots are there, or how many poles are there? Definitely s square plus k term is there, m s square plus k is there, or s square plus or if you equate that one equal to 0, then it will be minus k by m. S square is equal to minus k by m, and then there will be two roots of that one, so there will be two poles of that system. Now suppose for example you have been given the value of m is equal to 1000 kg, mass is 1000 kg, and spring constant is given by 2000 okay, Newton per meter. So if you put the value of m is equal to 1000 and k is equal to 2000 Newton per meter, then what you will get? So you will get basically, if you simplify it, you will get x of s by f of s is equal to 0.001 divided by s square plus 2. If you put the value like this, means here you have this gain constant factor, again constant factor equal to 0.001, and then s square plus 2. If you equate that one equal to 0, so you will get two poles. So what will be that? That is equal to this one, no? S square is equal to -2, and then s will be equal to if you take the square root of that one, so you'll get two poles. One will be at positive side and another one will be at negative side, and which will lie on the imaginary axis. So this system, okay, we have studied that when two poles are there on the imaginary axis, okay, what kind of this system is there? Whether this system is a stable system or unstable system or marginally stable system. Can somebody tell me?
Marginally stable.
Very good. Okay, if poles are lying on the j omega axis, no other pole is on the right side, then this system is said to be a marginally stable. Okay. Okay, so this system is marginally stable. Absolutely correct, right? I hope that you have understood this problem, how to find out the transfer function. Have you understood, or if there is any query? I'll be happy if I get feedback from your side. Otherwise, it will be one-way kind of thing.
Yes, sir.
Okay, fine. So, okay, we'll take one more. Okay, one more problem also. Don't worry about it. Okay, now suppose, for example, this is another this one problem. Okay, same problem is there, but here some friction is given here. Friction between what? Mass element and then this reference element, some friction is given. So this friction, generally friction is referred with the dashpot, right? Friction is referred with the dashpot. So this value of frictional coefficient is given as a C. Okay. Now, if you ask, or if somebody asks you that, okay, find out the transfer function of this system. So what you have to do? You have to draw the free body diagram of this one. Now see that this is the input force, and then what is the output? Output is nothing but the displacement S, X, right? Now there are three elements. One is basically spring element. One of the end of the spring element is connected to the reference. Another end of spring element is connected to the mass. Now this is the mass having coefficient M, and then there is a frictional force between this reference and this one. Okay, just imagine that this one railway bogie is there, and you know, but okay, there will be a friction between wheel and the railway track, right? So this kind of thing will be there, and then this is also generally friction is replaced with dashpot or damper, so which opposes the thing. So dashpot element is there. Now when you apply a force on this one, there will be opposite force offered by spring element. There will be opposite force offered by mass element. Also, there will be opposite force offered by this dashpot element. So we will consider this as a Fk, this as a Fm offered by this mass element, and then this as a Fc. So if you draw the full free body diagram of above this one figure, then see that on this mass element, there will be force from left to right, which is input force, and there will be force when you're applying force. So definitely this mass element will try to shift here, but because of this spring, it will pull, with the force Fk. Also, it will be having self opposite force that is given by Fm. So this is Fm, which is opposing to the this applied force F, and also this frictional force Fc. So see that the force offered by Fk, Fc, and Fm is in opposite direction as compared to applied force, right? So Fk is the spring force, which is from right to left. F is the applied force, which is from left to right. Fc is the opposite force, which is from right to left. Fm is also opposite force due to this mass element, which is from this one, right to left. Now, you know that total applied force must be equal to total opposing force. So total applied force is equal to F, and total opposing force is due to spring element, due to mass element, and due to frictional coefficient, that is dashpot element. So Fk plus Fm plus Fc. Now you know that Fk, how do you write the Fk? This force is directly proportional to x now, displacement. So you can write this one k into x of t here. Then what is this Fm? M into d2 x of t by dt square, or m into x double dot t. And what is this one? Force offered by dashpot element, which is directly proportional to the velocity. Velocity is nothing but dx by dt. So but what is the coefficient? C into dx by dt. So we can write here like this. F is equal to differential equation of above system. F is equal to, what is this? M, what is mass element? Okay, mass into this acceleration, so x double dot, and then this dashpot element c coefficient, and into velocity, that is x dot, plus k is nothing but the spring constant multiplied by displacement x. Okay, now if you take the Laplace transform both side, so what will the Laplace transform f of this one? F of s. Then what is the Laplace transform of this individual term? By assuming zero initial condition, m will be as it is, and since this is d2 x of t by dt square, so this is double derivative. Because of that, this s square term will be there, and because of x of t, this will be x of s. I hope that you have understood how this term has come from this one by taking the Laplace transform. Similarly, if you take the Laplace transform of this individual term, so c is constant, so it will come as it is. X dot is nothing but dx by dt, dx of t by dt. So by d by dt will be replaced with s term, simple algebraic s term, and x of t will be replaced with x of s, right? So this is the Laplace transform of this term. Now plus k into x. So what is, okay, this k will be as it is, and x of s will be as it is. Now, if somebody asks you to find out the transfer function, now transfer function, you have to identify what is the output and what is the input. Now here, for this system, basically input was force and output was displacement of that system. So x of t is the output and f of t is the input. So we have to find out x of s by f of s. So here we have this equation, which is okay, giving the relation between f of s and x of s. So if you take x of s common here, so x of s by f of s will come like this. So the transfer function of that system will be equal to 1 upon ms square plus cs plus k. So this is the overall transfer function of given system, right? I hope that you have understood how to find out the transfer function of that system, right? Now, see, if you consider different value of m, k, and c, like as 1000 kg, 2000 Newton, okay, Newton per meter, and then c is nothing but 1000 Newton per meter per second. So like that way. And then if you put these values m, k, c here, and then if you simplify, you'll get x of s is equal to, x of s by f of s is equal to 0.001 divided by s square plus s plus 1000, right? Now, here, if you simplify this one, okay, you will get complex conjugate poles, and those complex conjugate poles will be lying on the left side of S plane. So which will be having some real part as well as imaginary part. Now, this complex conjugate poles are there on the left side of S plane. So this system is a stable system or unstable system. Okay, because poles are on the left hand side of S plane. No, not a single pole is on the right side. So this system is absolutely stable, and above earlier system was marginally stable, right? Now this, consider the another example of this one. So this translational mechanical system, see that one end of spring is connected to the reference, another end is connected to mass element, one end of dashpot is connected to the reference, another end of this dashpot is connected to the mass, and then this mass is there. Now force is in this direction, right? So force is in the direction. So output, okay, input is force, output will be displacement. So definitely it will go in the, okay, system will try to move in this direction, but at the same time, mass will also offer reactive force, spring will also offer reactive force, dashpot will offer also reactive force. So if you draw the free body diagram, so this force, okay, if you consider the force in this direction, or like for example, if you are now in this direction, so definitely force will be in this direction. So this force will be, okay, I have drawn it in exact opposite, so this should be in this direction. And when you are, okay, having this force in right to left, so this fk will be from left to right, and then fb will be also from left to right, and fm will be also from left to right, because they are opposing to the input force. So definitely F will be equal to Fk plus Fm plus Fb, and then the transfer function of that system, if you solve this is just like as a previous example. So x of s by f of s will be equal to 1 by ms square plus bs plus k. Same kind of thing will be there, right? I hope that you have understood this problem, and today we'll stop here. If you have any doubt, okay, we have considered this one, translational mechanical system. In our next lecture, we'll start rotational mechanical system, and then after that, we'll see the analogy between electronic system and mechanical system, and then how we can design those electronics mechanical system in terms of electronics. So that we'll study in our next lecture. So if you have any doubt, you can ask the question.
Hello, sir.
Yes, please.
Sir, last week you told about the submission of assignment, first assignment.
Yeah. Actually, I forgot to give this one. Okay, add you people on the Google Classroom. So there you can submit the assignment. Yesterday, I was trying to create the Google Classroom, but I was not able to add the TY class. I don't know what kind of technical problem was there. So what do you do? Okay, you keep your assignment ready, and maybe today or tomorrow I'll assign you, and then 4-5 days I'll give you more, so you can submit that assignment, all of you people, right? I'll give the deadline for submission. Earlier, I think I have given the deadline up to Wednesday or Tuesday, something like that.
Sir, Tuesday. Yesterday was the last day.
Yeah. Yesterday was the last date, but I have not created this Google. I was not able to create the Google Classroom. There was some technical problem. I was trying to add TY class entire in the Google Classroom, but it was not accepting. I don't know why. So today,
other teachers just send us link and we will join by ourselves.
Okay,
but send us the link.
Yeah. Actually, that link. Okay, you can join there without adding this one.
Yes, sir.
Okay. Then what I'll do?
Send us the link and we'll join.
Okay, fine. Then today, actually, after this lecture, I have a meeting immediately. So maybe after meeting, I'll do that one. I'll send the link to join, and then you can submit your assignment there, right? But I'll give 2-3 days more for submission. Don't worry about it, right? So, anything else you would like to ask?